All right. Hello, everyone. My name is Jamie Kanehisa. I'm a PhD student at the Leibniz-Institut for Astrophysics. And in Marcel's research group, I work on testing the cold dark matter paradigm, specifically through the phase-space distribution of dwarf galaxies in the local universe. Following on from Marcel's discussion of the planet-satellite galaxies problem, I'd like to point your attention to another mode of spatial anisotropy, which is perhaps much less discussed, but still may pose a problem for the CDM model. Of the dwarf satellite galaxies of Andromeda, 34 out of 35 lie within a region just slightly larger than a hemisphere facing the Milky Way, which to me is an astounding degree of asymmetry. In this talk, I'll discuss the use of novel metrics to quantify this observed asymmetry. I'll compare the observed distribution to analogs in CDM cosmological simulations, and hence demonstrate that the observed degree of lopsidedness is highly rare in a CDM context. So, to recap, the study of dwarf galaxy arrangements serves as an excellent small-scale test of models of cosmology, especially CDM, since unlike the other so-called small-scale challenges, it is not alleviated by simply tuning baryonic parameters, mainly due to its much larger regime on the scale of hundreds of kiloparsecs. Of course, the most well-known example of this are the planet-satellite galaxies observed around the local group hosts, as well as a scatter of systems within and beyond the local volume. Crucially, these flattened and kinematic coherent structures have proven to be very unusual in a CDM context, mainly found at a sub 1% level, thus being very problematic for cold dark matter so far. Now, the topic of today's talk is the M31 system, which, even at first glance, demonstrates a very strong degree of lopsidedness towards the Milky Way. Past work has consistently shown that around 80% of M31 satellites, regardless of the dataset used, is in the hemisphere facing the Milky Way, and this is a statistic that's generally used when referring to this phenomenon. Indeed, lopsided satellite distributions have actually been found in other paired host galaxies in the local universe, generally demonstrating an asymmetry towards the companion halo, to an extent that the simple effect of overlapping satellite populations cannot fully explain. Their analogs have also been found in cosmological simulations to demonstrate a degree of lopsidedness that's roughly consistent with that of the observations. And interestingly, lopsidedness has also been confirmed around isolated hosts and their simulated analogs, indicating that this is not just a pair-only phenomenon. And yet, there has been no simulation comparison for the M31 system where it all began, despite its very prominent degree of lopsidedness for an individual system, as well as access to a large sample of relatively precise satellite distances due to the system's proximity. Now, this work was mainly motivated by the recent release of homogeneous Lyrae-based distances in Savino et al. 2022, which covers nearly all of the known M31 satellites within its CDM halo's virial volume to a distance precision of around 3%. Interestingly, some satellites previously on the far side of M31 now are thought to face towards the Milky Way, intensifying the existing asymmetry. Mirroring the author's analysis, we exclude the following objects, leaving us with distances for M31 itself, as well as 35 of its satellite galaxies. We now move to compare the observed system to analogs in hydrodynamic cosmological simulations. On one hand, we use the illustrious TNG suite's TNG 100 run, which is a hydrodynamic simulation with a box size of around 100 megaparsecs length, while still retaining enough resolution to resolve at least a couple dozen subhalos per M31-like halo. We also use the Eagle simulation's fiducial run, which has a similar volume and resolution to that of TNG 100. We first begin by finding analogs by their halo mass, then proceed to search for any companion halos it may have, which we then use to classify the simulated systems into isolated systems, which have no companion, and paired systems, which have exactly one. Any more, and we reject them. We then proceed to identify the satellite population of these, limiting it to exactly 35 satellites to match the observed sample and make sure we don't have any problems with differing satellite counts. Finally, we mock observe these systems by drawing distances from the M31 satellites as well as M31 itself and applying them in a Monte Carlo fashion. Now here's the question. How do we actually go about quantifying a lopsided distribution? The traditional hemispheric approach, in which you count the number of satellites in a given hemisphere, generally towards the Milky Way or some similar companion, would assume that this asymmetry is maximized towards the Milky Way, and in any case would fail to spot any smaller or larger concentrations of satellites. To solve this, we tested a total of 8 different metrics for lopsidedness, each exploring a slightly different aspect of asymmetry. But for simplicity's sake, in today's talk I'll only discuss 2 of them, what we refer to as the free and locked cone metrics. Now, the locked cone metric is in fact a direct extension of this traditional hemispheric approach. We generate cones locked in the direction of the Milky Way, hence the name, with opening angles anywhere between 1 to 359 degrees. And we count the number of satellites contained within each cone, which then serves as the direct output of this metric. And of course, since we require a companion direction, we can really only use this for paired systems in these simulations. On the other hand, the free cone metric does not have any such restrictions, since instead of locking cones towards a specific companion, we instead test a total of 10 to the 5 isotropically distributed directions. For each opening angle theta, we identify the maximum number of satellites contained within any of those 10 to the 5 cones, and as such serves as an excellent measure of the absolute asymmetry of a given system, with no preconceptions on which way it may be pointing. And of course, because of this, we can use this for both paired and isolated systems in the simulations. Now let's take a look at some of the results. This is the direct output of the free cone metric, with the opening angle and the corresponding max contained satellites on the horizontal and vertical axes, respectively. The red and blue lines indicate medians for TNG and Eagle, while the 1 and 2 super spreads of the simulations are shown in purple. And of course, the black line represents the M31 system. I'll note here that because we've implemented the distance uncertainties into these simulated systems, we don't need to consider any Monte Carlo approach for M31 itself, and thus have a clean line to work with. We can see that this M31 black line diverges the most from simulated expectations at around 202 degrees, containing 34 out of 35 satellites, the number I mentioned in the beginning. This occurs at 202 degrees and goes slightly beyond the 2 sigma region. On the other hand, this divergence is far stronger for the locked cone metric, looking at asymmetry towards the Milky Way or a companion. This is maximized at 213 degrees, also containing 34 satellites, but this time going far beyond the 2 sigma mark. Indeed, this distribution is so dramatic that it can also be expressed as a kind of void on the far side of M31, where only a single satellite, NZC205, inhabits. Now, here's the big question. How frequent are M31-like lopsided systems among their simulated analogs? This is exactly what we plotted on the vertical axis here as a function of opening angle, and we can see at that aforementioned 202 degree mark, less than 1% of simulated systems can match the observed lopsidedness. The situation is far more extreme for the locked cone metric, where at 213 degrees, exactly none out of nearly 20,000 simulated realizations can match the observed asymmetry. However, these results may be affected by something called the Look-Elser effect, which is a statistical phenomenon where an apparently significant result may simply arise by chance due to the size of the parameter space that was searched. In our case, our selected value of theta is an arbitrary one, and there may be simulated systems that are more significantly lopsided at other values of theta. To compensate for this, we hence use a significant space approach as follows. We first select a simulated system, or it could be an M31 system, and for each theta, we then find the fraction of a set of isotropically generated systems that are as lopsided as the given system in question. We then find the minimum across all theta, which yields that single system's minimum isotropic frequency, which we've plotted on this CEF here, while the black line indicates the single results for M31. Surprisingly, 7 to 8% of simulated systems do demonstrate a similar degree of lopsidedness at some value of theta. However, these numbers are far lower for the loss cone metric, only looking at asymmetry towards the Milky Way, where only 0.1 to 0.5% of simulated analogs can match the observed asymmetry in any capacity. Now, does this small sample of M31-like lopsided analogs demonstrate a population-wide asymmetry, like Andromeda does? That's the next question. Now, these black crosses here indicate those lopsided M31 analogs, with the result for M31 itself shown as the black and white circle. Each of these points, including the black crosses, represents a single simulated realization at its minimum isotropic frequency, essentially at its most significantly lopsided point, with corresponding opening angles and number of contained satellites on the two axes respectively. We can very clearly see that the M31 system demonstrates the strongest degree of population-wide asymmetry among its peers, while the few similarly lopsided systems and analog simulations, are mainly driven in terms of significance by much smaller groups or clusters of satellites. Crucially, Andromeda's asymmetry doesn't appear to be a simple artifact of observational systematics. Earlier this year, Delinsky applied the pandas survey's detection limits to isotropic realizations of the M31 system, and found that this still results in a 5 sigma discrepancy with the observed distribution. I'll note that they only required realizations to satisfy M31's hemispheric asymmetry, which, of course, is a much lower bar to satisfy than the population-wide asymmetry that we've discussed today. In other words, the lopsided distribution is a physical structure. Now then, how could such a structure be formed? After all, it's quite unlikely that such a well-defined lopsidedness is simply due to a chance alignment of satellites. In 2020, White et al. Explored the initial conditions required for an infall event of dwarfs to reproduce the observed lopsidedness. They found that, apart from requiring a very eccentric infall trajectory, this placed very narrow limits on both the size of the association falling in as well as its infall velocity or specific energy. Furthermore, the presence of any non-spherical halo potentials in the host, as well as the natural phase mixing of satellites, would weaken this symmetry dramatically over time, dissolving such a structure in timescales often as short as 500 megayears when the first orbits finish. As such, to reproduce the observed distribution, such an event would have been very recent indeed. However, the main problem with this hypothesis is that, of course, the M31 system is very well populated in its asymmetry. This leaves us with a kind of catch-22 scenario. Either this lopsidedness is due to a recent group infall event, in which case we're left with a catastrophic lack of older satellites, or this is a long-lived structure, which would bring into question how such a structure would have been survived for so long. In any case, we currently don't have any explanation, or at least definite explanation, of M31's lopsided satellite distribution, which, in conjunction with its satellite plane, is very problematic for the CDM model. Now, Unlike the satellite planes, Andromeda's asymmetry is actually also in stark contrast to the consistent but weak asymmetry that appears to be prevalent in other systems in our local universe. I'll refer you to those studies if you're interested in these specific details, but suffice it to say that M31, whose distribution is almost better characterized as a void on the far side, is the exception, not the rule. I'd like to point out some caveats here for these studies, however. The first being that their median satellite sample is quite low at only 3 to 4 satellites, and a significant fraction of them may be interlopers, satellites that are physically unassociated and lie in either the foreground or background. Because of this, it is currently very difficult to determine whether there are any other M31 Lake extreme systems out there. As the first step towards answering this question, I'd like to advertise some ongoing work in searching for lopsided satellite distributions in MATLAS, a survey mainly targeting early type host galaxies and their dwarf satellites with a much larger satellite population. This will be done in conjunction with a comparison to mock MATLAS-like fields in CDM simulations to determine whether any general discrepancy exists. This is being done in collaboration with the people here, including Oliver, who is in the room today. And with the benefit of a much larger satellite sample, we can hopefully tell whether, or at least get some better insight into the prevalence of both this weak and well-populated prominent asymmetry in our local universe. To conclude, I'd like to return to my main results. The Andromeda system demonstrates a very prominent degree of asymmetry, with nearly all of its satellites lying within a cone just slightly larger than 200 degrees. In cosmological simulations, I found that this lopsidedness is, especially towards the Milky Way, only matched by a sub 1% frequency of simulated analogs. Now, if there's only one thing that you take away from this talk, I hope that's this. The M31 system's lopsidedness towards the Milky Way is exceedingly rare in a CDM context and demonstrates a stronger degree of population-wide asymmetry than any of its similarly lopsided analogs. In conjunction with M31's well-studied plane of satellites, my results paint M31 as a very striking outlier in a CDM universe. Now, could this be solved by MOND is the question I would like to pose here at the end, since I have the privilege of standing before many MOND experts today, with the benefit of some external field effect perhaps from the Milky Way. Would it be possible to generate such a lopsided distribution? Might it be possible to explain this where cold dark matter seems to struggle? Thank you very much.
Very clear presentation. Yes, Stacey.
So, of course, I was wondering, your last question as you were speaking, this is very weird in line with CDM. Seems very weird to me in MOND offhand. It just seems very weird. Maybe there's some effect, but it seems just very weird. But something else you said made me think it's even weirder. You mentioned that the one that's on the far side is NGC 205,
Yes.
which is hardly a typical dwarf, right? It's
Yes,
very
it's
bright.
quite massive.
So, do you have any other thoughts about that peculiarity? I mean, all of the sort of the little dwarf are on the same side, all of them.
To be honest, I'm not sure about that. It does seem at first glance like that major satellite is dominating the sample, but we'll need to do, well, this is the problem is because I can't personally think of any valid formation mechanism that would create a situation like this. It's impossible to test scenarios because we can't think of any potentially viable one.
It's weird on top of weird. Did you want to comment on
Yes, there's.
I just wanted to ask a question about the simulations, in the sense that when you compare the Milky Way system with the simulations, what are the typical characteristics? Like how do you identify Milky Way Andromeda analogs in the simulations?
Right, so I believe, so this is the detailed flowchart I use for selecting analogs. So it's somewhat a wide range. It's not necessary that they're very close to what Andromeda is, but they're within the vicinity. And yeah, we're mostly looking at whether any a mechanism could cause something like this, because any mechanism like that wouldn't be restricted to exactly the M31 mass, or it could be something around that. But hopefully that answers your question.
It was really, really good presentations. So I think in MOND it's possible indeed to explain this with a star field effect, but at such level it might still be complicated because you need to get a really strong asymmetry in the cases. And I was wondering, like also a question for the audience, that either in MOND or in ΛCDM it's still possible, well maybe more in ΛCDM in that cases, that the M31 is completely outside the barycenter of its dark matter halo in the cases, or to the center of the field of potentials. But to my knowledge, there is not such a big accretion, a big source of attraction, right, in there. So do you have any thought about this?
So wait, are you talking about an offset of the actual galaxy from
the center of its barycenter of dark matter?
So among the 8 metrics I discussed, there was one that specifically searched for that. And the main message I got from that with the simulations is that this offset is there, but it's not anything special. It's I believe, within 10% of simulated analogs, so it's definitely more offset than usual, but definitely not enough to explain this prominent asymmetry.
So if you have to move the center of M31, so it's as a barycenter, let's say, of the center of the galaxy, so you have to have a completely uniform distribution. Where should it be located in terms of
Oh,
distances?
I see. I haven't tested that directly. I have looked at different M31 mass estimates, and of course, if you bring M31 closer, it would help resolve this. I mainly focused on the Sabino et al. Distances because it's made using the same method, roughly, as the homogeneous satellite sample, so it seems the most reliable. But I don't know the exact distance. I can get back to you on that.
Actually, we have to rush along. There's a poster now